Hello, I'm Jonathan Aldrich, and today we're going to get a little bit formal and talk about dynamic semantics. Semantics gives a language meaning. It does so by forging a connection between the abstract syntax tree of the language and something else that already has meaning. One possibility is to relate the language to using natural language semantics. So, for example, the Java language specification is a long document written in carefully structured English. Unfortunately, the Java language specification turned out to be ambiguous when it was describing the Java memory model, which is very important for concurrent applications in Java, and this required substantial research to fix. Another possibility is to use mathematical definitions, or formal definitions, as we sometimes say, in order to specify the language. An advantage of mathematical specification is that we can make it fully precise and unambiguous. What this does is it enables designers to reason about the language to make sure that their design is a good one. It also enables implementers to make sure their implementations are correct. One recent use of formal language definitions was to specify the WebAssembly language, which allows executing programs very efficiently within web browsers. Let's talk about dynamic semantics first. As we discussed earlier, dynamic semantics specify the meaning of a program by defining how it generates outputs from a given set of inputs. Our approach to defining dynamic semantics will be operational semantics. These show how the program operates, as the name suggests, via a step-by-step computation model, basically the way an interpreter operates. Other kinds of approaches are possible. For example, a translational approach to specification reflects what happens in compilers and in fact can be used to specify a compiler. And we'll look at that again in chapter 15. Denotational semantics are very useful for certain proofs about languages, and axiomatic semantics can be useful in reasoning about programs. Moving forward with operational semantics, we're going to define evaluation as a mathematical judgment. A judgment is just a mathematical statement about a program. In this case, we're going to use an evaluation judgment to relate an abstract syntax tree to the result of evaluation. So here's a simple judgment form for evaluating calcular expressions. We take an expression e and we evaluate it down to some value v. The evaluation is expressed with the down arrow in this judgment form. This judgment will be called eval. Here's a concrete instance of this evaluation judgment. Basically what we're going to do is we're going to plug in an expression for e and plug in a value for v. Here, the expression will be a binary operator. Here we're defining expressions with an abstract syntax tree. So the abstract syntax tree has a binary operator, which is plus. It's adding two integer literals, intlit1 and intlit2, and it's evaluating them down to an intlit of 3. We call e and v metavariables because they stand in for parts of the program text, whereas a regular variable would be just a variable in the program text. And what we substitute the metavariable e with is a concrete AST expression, and for v it'll just be the subset of ASTs that represent values. These come from our abstract grammar for expressions. Formally, values are the subset of expressions that are constant literals. In our little calculator language, we have integer literals and real literals. So v is either an intlit of some mathematical integer n, or a reallit reflecting some mathematical real number r. Or in an implementation, it would probably be a floating point number. The meaning of the judgment that I just showed is, of course, very simple. The expression 1.2 evaluates to 3. Now, we could easily write judgments that are false. For example, the judgment that says, oh, if you apply the binary operator plus to 1 and 2, you get 4. That would be a false statement, right? So how do we know it's true? Well, we can use inference rules to define which judgments are true. An inference rule is written with a line with the conclusion, the thing we want to show is true, at the bottom of the line, and at the top of the line we have premises. The premises are judgments, the conclusion is also a judgment. And what the judgment means is that if all of the premises are true, then the conclusion is also true. We give each rule a name and we put it beside the side of the rule so we can refer to the rule. Let's start by writing a simple inference rule for literals. We define the literal evaluation with the rule that says that every literal simply evaluates to itself because it's already a value. And we'll call it the ev-lit rule for evaluation of literals. This is a special kind of inference rule called an axiom. Axioms are inference rules that have no premises. Now, this rule is true for all values. We can instantiate the rule with any particular value, basically by substituting the metavariable v with that value everywhere it appears in the rule. For example, we can conclude that the integer literal 3.14159 reduces to itself, integer literal 3.14159, and we do that by substituting v consistently with the value intlit 3.14159 everywhere. We have to be consistent because, of course, we don't want to say that pi evaluates to 1 or anything like that. It wouldn't be true. So the consistent substitution makes the rules work. Let's give an inference rule for integer addition. Here we say we're evaluating the thing on the bottom, right? The bottom part is the conclusion. That's the judgment we're trying to establish. And what that conclusion says is that we want to evaluate some binary expression e1 plus e2. So how do we do that? Well, we need to check if the premises are true. So the first premise says that expression e1 evaluates to an integer literal of some integer number n1. And then e2 similarly evaluates down to an integer literal of n2. We then check what do n1 and n2 add up to. And here we just use a mathematical expression, right? n1 plus n2 is some number n3. And so math will tell us which number n3 is. If n1 is 1 and n2 is 2, then n3 will be 3. And so then, if all those premises are true, then the conclusion says that the binary expression binop of e1 plus e2 evaluates to n3. Now, the third premise is not actually a judgment. We're just referring to mathematics. We could actually formalize that as a judgment with inference rules, but we won't do so here. We're just going to build on our existing knowledge of mathematics. Let's clean up our notation a little bit. So if we look at that rule for integer addition, it's very careful to represent abstract syntax tree elements very explicitly, right? So intlit of n1 is an AST element, n1 is a number in the concrete syntax of the language, and if you look very carefully, the rule writes n1 in the mathematical expression in italics to represent that n1 is the mathematical integer that corresponds to the integer literal n1 in the text. So it's only mathematical numbers that we can actually add up to. We're going to simplify our notation a little bit, however. Really, wherever intlit appears, we just know we're just going to treat it as if it was a mathematical number. So remember, under the hood, it's all abstract syntax trees, but we're going to make the rules a little bit cleaner to write by saying, okay, the expression e1 evaluates down to some number n1, e2 evaluates to n2, and then, of course, n1 and n2 evaluates to e3, and so we have the conclusion. We can write a similar rule for addition on the reals. Here, e1 evaluates to some real number r1, e2 to r2, r1 plus r2 is r3, and so a binary op on e1 and e2 can evaluate to r3 if e1 and e2 both evaluate to real numbers. Together, these rules show how we can define evaluation in terms of mathematical judgments. Now, a little side point on the semantics of inference rules. We've been defining the rules in a kind of intuitive order. So above, the first premise evaluates e1, and then we'll evaluate the second premise e2 because it seems natural to evaluate the second expression next, and then we do the addition last. In the semantics of inference rules, though, the order doesn't matter. It's just a mathematical statement. So it would actually mean the same thing if we put the premises in a different order. I mention this so you can understand that it doesn't matter, the order of the premises, but we'll continue to write the rules following the intuitive order of evaluation just to make them more readable. Now, once we have these rules, we can compose multiple rules into what's called a derivation that shows how an expression evaluates. A derivation is a tree with the thing we want to conclude at the bottom. Here, we're using a binary operator on two real literals, and we're applying it to evaluate it down to some final real number. Now, to evaluate this, the binary operator rule, ev add r, has two premises, right, for the expressions e1 and e2 plus this mathematical premise. And so the branches of the tree show how to compute those premises. In this case, the tree is very short. We have one rule at the bottom, and then there's two branches with one rule each. They're actually leaves coming right off the trunk of the tree, I guess, in this analogy. And so in this case, the tree shows that the first premise of binop is reallit 1.2 evaluating to 1.2. The second premise is reallit 2.3 evaluating to 2.3. Those are both applications of the evlit rule. And then, of course, 1.2 plus 2.3 is 3.5. Again, we don't need to use rules to prove mathematical premises like 1.2 plus 2.3 is 3.5. Statements like this that we just get from math are called side conditions, and we use our knowledge of math to check them instead of using inference rules. So what are the semantics of derivations? Well, we say a derivation is complete if every judgment is proved with a rule or is a side condition that we can justify using mathematics. So a complete tree is one with no pieces that aren't filled in, right? There's no judgments that we haven't proved yet because everything has been proved with a rule. And so a judgment, we say that is provable if there's some complete derivation tree that proves it. And of course, the judgment we saw in the last slide is complete because for every judgment, there's an evaluation rule that proves it. So this is nice, but we can see that this notation is still perhaps a little bit more complicated than we would like, right? We still have real literal, we still have binop in the AST, the program. There's lots of details around the AST structure, and as long as we remember that we're representing an abstract syntax tree, we could actually simplify things somewhat. So we're going to use a language-like notation shown on the right. Here's the diagram from a previous lecture on where we introduced abstract syntax trees. You'll remember that on the left we have an abstract grammar that says E can be a variable node with a variable x, an integer literal, and a real literal r, float, trunk, binop. That gives us a data type which represents these in a data structure, in this case in pseudocode, but something very much like this might work in a real programming language. We're going to use a notation on the right to represent each of these cases. So a variable x will be just represented with x, a number n, an integer literal n will be represented with n, a conversion to float we'll use the expression float e, and of course for binops we'll just use e1 op e2 for whatever the op is. So this will be a cleaner notation. Now we can write our larger derivations in a much cleaner way. So evaluation of literals now we're representing the integer literal of 1 just with 1, and so 1 evaluates to 1 with evlit rule, 2 evaluates to 2 with evlit rule, 1 plus 2 equals 3, and now we can compose this as part of a larger expression to say that 1 plus 2 plus 3 equals 6 by applying another version of ev add n. Notice here that we have a deeper tree, right? We have 3 levels, but the structure of the derivation follows the structure of the expression. And that's because we basically wrote an evaluation rule for each grammatical construct. So we have a grammatical construct for adding 2 numbers together, and we have an add rule that corresponds to that. And so we just break it down into pieces, and the structure of the tree follows the structure of the expressions. This is commonly true for evaluation in simple formalizations of programming languages. In more complicated languages, it might not be a one-to-one correspondence, but this is a good practice when you can do it. We can make things a little bit more general. So you might have noticed that our 2 add rules are very similar. One is for integers and one is for real numbers. But we can combine these. All we have to do is check that the types are consistent. Right? So it might not be totally clear what happens if we add an integer to a floating point number. Well, maybe we could guess at what that means, but our actual machine is going to use different instructions for that. So I'm going to require that the types be the same in this language definition. And so we have an ev add rule which will replace both our integer add rule ev add n and our real add rule ev add r. And so what this rule says is e1 evaluates to some value v1, E2 evaluates to some other value v2. We have only 2 types in the language, ints and reals, but we need to make sure these 2 are the same so that we can apply either real addition or integer addition to them. So we'll assert that type of v1 equals type of v2. And then v1 plus v2 equals v3. That means that e1 plus e2 evaluates to v3. If we want to be very precise, we should define what this type function means. In this case, it just means if we apply it to an integer literal, then we get int. If we apply it to a real literal, we get real. We can further generalize to support not just addition, but any kind of operator. And so what this rule does is it says we're going to have a symbol, here it's the little circle plus, that stands in for any mathematical operator. So circle plus could be plus, minus, times, or divided by. And so when it's in the conclusion at the bottom, we're saying the circle plus appears in the source text, and when we use it in the mathematical premise, we use the corresponding mathematical operator, so division for slash. Like the generalizations we described that unify integer arithmetic and real arithmetic, this just allows one rule to represent more of the semantics, right? We could write 4 separate rules for plus, minus, times, and divided by, but that would make our specification long, and those rules aren't interestingly different. So we just write one rule that covers all of them in this slightly more generic way. Let's finish the semantics for our little language. We're going to leave out variables for now, but we'll do the other ones. So we want to convert between integers and reals. So in our little language, the way that you add an integer and a real is you convert the real to the integer or the integer to the real. So our language has a float construct, and the semantics of that says float of e evaluates by first evaluating e to some value n. That's the first premise. And then we're going to say toFloat of n equals r. Notice that implicitly when we say e evaluates to n, we're claiming that the result of evaluation is of the form n, right? N means intlet of some natural number. And so the float rule can't be used if e evaluates to some real number. And that's what we expect, right? We expect the float operation to convert from an integer to a floating point real number. We're going to assume that there's a helper function toFloat, which applies to any integer value n and gives us a real number back. And that does the real work. Now, we could define the semantics of those with inference rules, but you can imagine that the conversion between integers and real numbers might be a little bit complicated and hard to write down. And so we're just going to assume that that exists. It isn't necessarily valuable to do so in our semantics. It's just complicated to write down. So it's pretty common to use things like this for constructs that are in this category, and we'll implement them as built-in constructs in the compiler, or maybe calls to routines that are written in assembly language if there's some interesting computation going on. We can define a similar rule for truncation, which takes a real number and truncates it to an integer. Let's check our understanding. Here, show a derivation that for the evaluation of the following expression, 2.718, or e, as some people know it, plus float of 1. You can use all the rules that we just described. I've given you the latest version of them, including the generic binop. Take some time, get out a piece of paper, write a derivation, and you can check your result in a minute.